Okay, so welcome back. In this video, maybe a couple videos, I'm not sure, we're going to do a real world project. And it's a project I wanted to do because of this device here. And you may be familiar with it. It is a USB battery bank, and it's used to charge cell phones or whatever. And you can see it's got two outputs and an input for charging. And it's got an on-off switch. Turn it on, and I think you can see the lights show that it's 4 bars, full battery, and you press it twice and it turns off. So this is a real nice device. It is a 10,000 milliamp hour or 10 amp hour battery, and of course it's USB, so it provides 5 volts. And it's 5 volts out and 2 amps out maximum. So it's got fairly good capability. You can get 5 volts, 2 amps, and 10 amp hour. So you can run 2 amps for 5 hours. You can use it for bench projects. You can use it for whatever you want. And I really like this, and it's a nice portable thing you can use if you need 5 volts. One of the characteristics of this particular device, not all of these, but if you've seen them before, if you turn it on, like I press the button, turn it on, and you connect something up to this output, and you're feeding 5 volts, say, to your circuit or something, and if you are running that at a very low current level, this device internally has some logic to sense whether it thinks there's anything connected to the output. So like now, I turned it on with nothing connected to the output. It's going to say, hey, wait a minute, there's nothing connected. Why am I running? And it's going to shut off in about 30 seconds, 35 seconds. We'll see this thing turn off. There you go. It turns off automatically. So if you have it connected to insufficient load, it will shut off just when you don't want it to shut off. So now some of these devices have when you press twice, it will put it into stay on forever mode. This one doesn't have it. You press twice and it shuts off completely. So my problem was I wanted to keep this on even though there was not enough current. So what we're going to do in this series or this video is we are going to design and simulate and breadboard and build a device that will keep this on. It's basically going to fake the internal logic and make it think that there is continuous load connected. And we're going to figure out how we're going to do that, and we're going to make a little device to do that. Okay, so our USB battery pack, we said, is 5 volts DC out, 2.5 amps rated output, and 10 amp hours or 10,000 milliamp hours. Now, after doing a little testing, I found out, and we saw in the opening here, that it shuts down in approximately 35 seconds unless there's load applied. And my testing showed that it has to be about 100 to 150 milliamps of load. So that's 0.1 to 0.15 amps of load, or else this thing is going to shut down. So somehow we're going to have to apply that amount of load current to this device to keep it on. We're going to have to fake it somehow. Now, I also did some other testing and found that the load can be on for only about 5 seconds in the 35-second time it takes to sense if something's on. So if we have it on for 5 seconds, then shut it off for the remainder of the 25 or 30 seconds, we should be good to go. So all it needs is a 5-second pulse of load, 100 to 150 milliamps load, in a 25 to 30 second period, and it will be fooled into staying on. So that kind of says we're going to need something in terms of duty cycle, about 10 to 20% duty cycle on applying load. So now we're starting to see what we're going to need for a design. Design parameters, we want a small 5 volt circuit, okay? And we don't want to, this is not a big deal. This is just something we want real quick and easy to fake this thing into staying on. So when we see duty cycle of about 10 to 20%, we might think, well, let's do pulse width modulation with maybe 5 seconds on and 20 seconds off, something like that. It doesn't really matter. I mean, at the end of the day, you could just put a resistor and you're good to go. It's just that you're wasting amp hours. So, pick a number and say 5 seconds on, 20 seconds off, something like that. And then you apply a 150 milliamp load for those 5 seconds when it's on, right? So, ballpark, it doesn't really matter. You don't have to be accurate here. And we don't want any external inputs except for 5 volts DC. We just want to plug the USB out from the battery into this thing, and then the output just goes right to your load. So we don't want any, PWM inputs or anything like that. We just want it to run on its own using 5 volts DC. We also want to use whatever parts are lying around. I mean, this is not something that's critical. We just want something to get by. So if you start to think about it, you might think, well, what do we want for output? Well, we said we want a PWM that turns on a load for 5 seconds, then off for 20. So you might be thinking, well, maybe we have like a Mosfet or a transistor, and you gate it on with a PWM, and that turns it on, and maybe he's got some kind of resistive load or something here, 150 milliamps load, PWM, you've got 5 volts plus and minus, and you need some sort of circuit in here to take from the battery bank and convert that into a PWM to feed into the gate of a Mosfet or transistor, whatever you want. Again, this isn't a high power application. 150 milliamps is pretty much peanuts. You can use transistor, Mosfet. But again, we said whatever parts are lying around, we'll just throw something together. So you can see we're probably going to be talking about something like this, and then some sort of circuit that generates a PWM on its own. So what I looked around for some components, and I found, like many people probably will find, you've got a 555 timer hanging around because they're so popular and so useful. So what I'm going to do is use a 555 timer. And I also found some Mosfets. I didn't have any transistors, so I'm going to use a Mosfet, IRF 510 for what that's worth. It can handle gate voltages around 3 volts, something like that. So we should be good. So these are going to be my main components. We just need to figure out with the 555 timer how we're going to get it to run all by itself with 5 seconds on and 25 seconds off, right? So the 555 timer, if you look at the spec sheet, and here is the spec sheet for the 555 timer. And here's all the stuff. We don't really care. Here's the internals. You can look through. Here is a basic block diagram of what's in it. It's got some comparators, flip-flops, transistors, voltage dividers, that kind of thing. We don't really care about that right now. We're going to look at the electrical characteristics, 5 volts to 15 volts, so we know we're good. Those are typicals. It can go from supply voltage 4.5 to 16, so we're good. We're right at 5. So we're going to want to generate something like this plot here. And basically what this 555 is going to be working, the principle it's going to be working on is just like an RC timer with RC, resistive capacitive time constant, charge up and discharge time constants to define the on and off time, okay? So the big player here is going to be a big capacitor that you charge it up and then discharge it. And the time constants of the charge and discharge define how much time the PWM is on and how much it's off. And it's going to look just like this. We're going to have a little bit different because we're going to have a very short on time and a very long off time. But it's going to be basically, you're going to have a big capacitor that's going to be doing all the work, and all the rest is just to support that. Now that is called an astable multivibrator, all right? It's astable because it's going off on its own. It's just generating these signals. You're not controlling it externally. It's just generating this PWM based on how you set up the capacitor and the resistors and the time constants. Now you can also vary this. You can have variable resistors. You can have a potentiometer if you want to vary the time constant. We don't really need that. We just need some fixed values to set up like a 20, 15, 20% duty cycle, and we're good to go. Again, you can do whatever you want. You can have a potentiometer, but we're just going to stick with something like this. Okay, so here I am in LT Spice, and I've set up a Stable Multivibrator using a 555. I'm not going to go through all the details of how you do this. I'm going to assume you know how to do LT Spice. There are many sources of information on the net about 555s and different ways to set it up. This is a very common way to do it. So I've basically taken that, and I'll show you some of the basic components of this. You can just copy this, do whatever you want, but I'll show you how to set it up. So the big player here is this NE555. And this is included in LT Spice. If you go up here into the components and you go to the MISC folder, the miscellaneous, there's an NE55 model you can just drag and drop. So it's all set to go. You don't need to do anything. And the next big component I'm going to use is a Mosfet. And again, I said it was an IRF 510 just because it's one of the Mosfets I have hanging around. Now, of course, you can use whatever you want. I just had that. I downloaded the model and set it up. It really doesn't matter that much. So the big players are this Mosfet, which when it's on, it feeds current through this resistor and provides the 150 milliamps or whatever load to this 5-volt DC supply. And here is the battery pack. And you're basically taking the output from the USB of the battery pack and applying this across that output. And then from here, you're going to go out to your load, whatever you're supplying. So here's your 555. The output is going to give you the gate input, basically the PWM into this to turn it on for 5 seconds and off for 20. Now, this can look kind of complicated, but it's pretty straightforward. This capacitor down here is the really important player, all right? In this case, I've got a 1,000 microfarad capacitor. And like I said before, the whole point of this is to charge it at a certain rate and discharge at a different rate. And those two rates define how long this 555 output is on and how long it's off to provide the pulse width modulation. Now, there's two paths here, okay? These two diodes define the two paths. Now, when you charge the capacitor, you will go through this path, okay? So the positive is going to go through this diode, through this 1K ohm resistor, and charge the capacitor, okay? Now, when it's charged, you're then going to go through discharge, and it's going to go through this 10K in this direction and discharge through the discharge pin, okay? So basically you would expect, as we showed in the previous slide, the voltage across this capacitor is going to charge fairly quickly and then slowly discharge. And that's going to define a short duty cycle, a 10 or 20% duty cycle, because you're charging quickly and then slowly discharging. And the way you're doing that, you've got a 1K to charge and a 10K to discharge, all right? So a big time constant, a 10K RC time constant to discharge, and a 1K short time constant to charge it. Now, you can, in this box, this dashed box, you can make this a potentiometer if you want to vary it. And there's circuits out there. Basically, you take the wiper, you connect these two across the full potentiometer and take the wiper and connect it here. Whatever you want to do. I'm using a fixed value of 1K and 10K, and that gives me what I need for the 15% duty cycle or whatever. Okay, so pretty straightforward. You've got the ground, that's straightforward. You got the VCC here. You've got the charge and the discharge. You've got the trigger, threshold out, reset going to VCC. Again, I'm not going to go into all the detail about this. It's pretty straightforward. It's just a charge and discharge cycle that defines the pulse width. And at the end, you're going to get, hopefully, a pulse width modulated voltage across this load. So again, a stable multivibrator. Let's run this and see what we get. So I'm going to check the voltage on the output, and you can see, there you go. Beautiful. So it starts at from 20 to 25 seconds, it's on, providing a load across this resistor. And then from 25 to 40, that's about 15 seconds off. And then it's on for 5. So it's 5 out of 20. And again, you can vary these values of resistance to change this. But it's 5 out of 20. So that's 25% duty cycle. You can tweak whatever you want. Now let's also measure across this big capacitor that's doing all the charge and discharge and see what it's doing. You can see, okay, it discharges to turn it on, and then as it charges up through this diode, it charges up, and then it reaches a certain point, it starts the discharge cycle and turns off. And now it's going through this diode to discharge. And there you go. You've got your output in a 20-25% duty cycle. Okay, so I think what I'm going to do is split this into 2 videos. In the next video, what we're going to do is we're going to actually breadboard this. And we're going to measure some of these values. And I'm going to show you using my data acquisition unit, because it's kind of difficult with the scope. These are such long times, 20, 30 seconds. I'm going to use my data acquisition unit with my homegrown software and look at these waveforms over a long period and, tweak it. And I think I'll also set up a variable resistor potentiometer to vary duty cycle and show you how that's done. So hope this helps. Take care. Have a really good day. Thanks.